Welcome to the very first explainer in our computer architecture series. We're going to pull back the curtain on the incredible magic that happens inside the devices you use every single day. And we're starting right at the heart of the machine. All right, let's get into it. Here's our game plan. We'll kick things off with the one little chip that started a revolution. Then we'll get into the crucial difference between a blueprint and a factory. After that, we'll peek inside the instruction set that rules them all, see how these processors are actually built, and then we'll tee up what's coming next time.
You know, to really understand any of this, we have to go back, way back, to the very beginning, to the birth of the modern computer's brain.
So what you're looking at right here is the Intel 4004. Now, back in 1971, this was the first microprocessor you could actually go out and buy. And believe me, it completely changed the course of technology. Before this little guy, computers were massive, room-sized beasts. This put all that power onto a tiny slice of silicone.
So, what is a microprocessor really? Well, it's pretty simple. It's an entire central processing unit, the brain of the operation, shrunk down and squeezed onto a single chip. All the logic, all the number crunching power, just miniaturized.
And the evolution since then, it's been absolutely breathtaking. We went from that first 4-bit 4004, and by the 90s we were into powerful 32 and even 64-bit processors like the Intel Pentium. But in the modern era, the game changed completely. The focus shifted from just making one processor core faster and faster to packing multiple cores, basically multiple CPUs, all onto one chip.
Okay, so all this rapid change brings up a really, really important question. I mean, if a chip from 1993 is so wildly different from a multi-core beast today, how on earth can they both run the same software? How do they all speak the same language?
The answer, well, it lies in one of the most elegant and crucial ideas in all of computer science, this separation between the job that needs to be done and the actual machine that does it.
This slide right here, this is the key to everything. We have two totally distinct concepts. First, you've got the ISA, the instruction set architecture. That's the what. It's the blueprint, the official rulebook that says, hey, these are the commands this processor must understand. And then you have the microarchitecture. That's the how. It's the physical factory, the specific layout of circuits and transistors that engineers come up with to get those commands done. So let's see how this all works. We're going to start by taking a closer look at that blueprint, the what, the ISA. The ISA is what we call an abstract model. The best way to think about it is like a contract, a binding agreement between the software programmer and the hardware engineer. It's a guarantee that if the software sends a specific command, the hardware is going to know exactly what to do with it. No guesswork.
So what's actually in this contract? Well, it defines a few really key things. First, the basic operations the CPU can do, stuff like add these two numbers or subtract that one. It also defines the parts of the processor a programmer can see and control, like its short-term memory, which we call registers. And most importantly, it defines the precise, unambiguous meaning of every single one of those instructions. Okay, so if the ISA is the blueprint, let's switch gears and talk about the how, the microarchitecture. This is the physical factory that actually brings that blueprint to life.
The microarchitecture. This is where the abstract ideas of the ISA meet the cold, hard reality of silicon. This is the hardware designer's playground, where they get to figure out the most clever, the most efficient, the most powerful way to build a physical machine that follows all the rules laid out in that ISA blueprint. And this image just brilliantly shows you how ridiculously complex that factory can be. I mean, you're seeing multiple cores, different layers of super-fast memory called caches, all kinds of specialized logic units. It's an incredibly intricate design, but every single tiny piece of it is there for one single reason: to execute the commands from the ISA as fast as humanly possible. So here's how this all comes together in the real world, with stuff you can actually buy. The x86 ISA is a famous blueprint. It's used in most PCs. Intel builds factories to follow it, like their Alder Lake microarchitecture. But so does AMD, with their completely different Zen 3 factory. And they both run the exact same x86 software. It's the same deal in the mobile world. The ARM ISA is the blueprint for most phones and tablets. Apple builds their M-series chips, and Qualcomm builds their Snapdragon chips. Two totally different factories, both following that same ARM blueprint. So the most important thing to take away today is this fundamental split, right? We have the rulebook, the ISA, and we have the physical machine that follows those rules, the microarchitecture.
And because of that blueprint, we have this common language. It's what allows your software to run on totally different hardware, even hardware built decades apart.
But that leaves us with a really fascinating question, doesn't it? We've got the list of commands, the instructions, but how does the data actually move through the processor? How does a chip physically carry out a command like add? That is what we're breaking down next time when we explore CPU execution models. I'll see you then.